is just going to be 1 there, so we have 2 minus 1. So here we're going to have 1 being equal to 1 this side. So this simply means that this is true for n equal to 1 like this. Okay, so we go to the second step, which is the inductive hypothesis. So we just say inductive hypothesis there. Okay, so inductive hypothesis, just like the previous examples, here we make an assumption, or we assume that the statement is true for n equals to k. So here we just make an assumption that the statement is true for n equals to k. So there's no need of solving anything here. So you just get the expression the way it is here. So we have 1 plus 5 plus 9. So 1 plus 5 plus 9 plus dot dot plus open brackets 4. So wherever this n, we substitute with a k minus 3 being equal to k open brackets 2k minus 1 like this. Okay, so the right hand side of this expression that we have here is our s subscript k. So we'll use it in the next step like we did in the previous examples. Okay, so now the next step there is we need to show that if we add the new term to the left hand side that we have this side here, and we move a step further, that's going to be k plus 1. So meaning that even on the right hand side this side, where there's k or where there's n there, we're going to put k plus 1. So now we need to show that when you add the new term, the statement, there's still going to be consistency in the statement that we have there. So meaning that here we need to also show that. So we need to show that the statement is also true for n equals to k plus 1. Okay, so basically here what we're simply just doing here is we're showing to say that sk plus 1 is simply equal to sk plus a new term when you add a new term this side, which is the ak plus 1 term there. So now this side here, we're going to write the expression the way it is there. So we have 1 plus 5 plus 9 plus all the way up to we have a 4k minus 3 first there. Then when we add the new term to this here, where there's k here, since we've moved a step further, we're going to say k plus 1. So meaning that we've moved a step further to the right there. So meaning that here we're going to have 4 open brackets, we have k plus 1 minus 3 being equal to k plus 1 open brackets 2k plus 1 minus 1 like this. Okay, so basically when you look at these expressions that we have there, you are going to notice one thing, that starting from the first term that we have here all the way up to the k term this side here, this gives us the sk, which is the right hand side of the second step that we have this side. So then this term that we have here, this is the new term that we've added to the already existing terms that we have there, which is the ak plus 1 term. Then the statement that we have, or rather the expression that we have on the right hand side this side, this is our sk plus 1 term like this. Okay, so now what we just need to do here is to show that there's consistency even when we add the new term there. So meaning that here we're going to add this and this together to give us what we have on the right hand side. So meaning that what is sk here, we're going to substitute with the right hand side of the expression on the second step there, or on step number 2 rather. So here we're going to get our k open brackets 2k minus 1 plus if we expand this new term that we've added there, that's going to be open brackets, that's 4k plus 4, So 4k plus 4, let me just erase that and write it nicely. Okay, so here we have our 4k like this, plus 4 minus 3 like this, being equal to this side. We can just also expand what we have there. So we have our k plus 1, then that's 2k plus 2 minus 1 like this here. Okay, so now let's go ahead and prove this statement there. So here, if we distribute this k throughout here, we're simply going to have 2k squared minus k plus, we get rid of the brackets here, so that's going to be 4k plus 1, because 4 minus 3 is just basically 1 there, being equal to this side. For now, let's keep it the way it is. So we have 2k there, so 2 minus 1, that's going to be plus 1 like this here. Okay, so now we add the terms that we have this side, so that's going to be 2k squared plus 3k plus 1. Then if we expand what we have this side here, you notice that we're going to have a k times multiplied by 2k there, so that's going to be 2k squared, k multiplied by 1, that's going to be k, plus 1 multiplied by 2k, that's going to be 2k, then 1 by 1, that's going to give us 1. So you notice that here we have our 2k squared plus 3k plus 1 being equal to 2k squared plus 3k here plus 1. So if you want to factorize this here, you're simply going to have this side, you're going to have k plus 1 and also 2k plus 1 there, which is the same thing this side, which is k plus 1, and you also have 2k plus 1 like this here. So now here we've shown to say that s subscript k plus 1 is equals to sk plus ak plus 1. So meaning that here we've shown that sk plus a subscript k plus 1 is simply equal to s k plus 1 like this here. So here you can just say therefore true for n equals to k plus 1 like this here. Okay, so now if this is the case here, so you can just say the given statement holds under mathematical induction. For all positive integers n there. So n can be any positive integer there, so it holds there. So meaning that here we've shown to say that that statement that we have there is true for n equals to